Welcome to our problem solving session. We are group 30 and we will be solving problem 8.38. And as you can see here, we have it drawn up for you. We have a beam that's supported by a fixed support at the end on the left. We have an internal hinge at B. At point C, we have a roller, and then it cantilevers out where we have a 5 kilonewton meter moment acting on it in the clockwise direction. And we are going to find theta B left, theta B right, and delta D. Hey, welcome back. And we are going to go ahead and find the forces at the supports for you. What we did was we took the free body diagram and we split it at the hinge at B. We're going to start over here on the right. And what we did was we said that the sum of the moments at C is equal to the minus 5 kilonewton meters applied at the end over at D. And then that's going to be minus the 5 meters times By over here on the left. And that all equals 0. And when you solve that, By equals 1 kilonewton going downward. And then we took the forces in the Y, and we said that the minus 1 kilonewton from By plus Cy must be equal to 0. So therefore, Cy equals 1 kilonewton going upward. And then just for the sake of thoroughness, we said the sum of the forces in the x is equal to B of x, which is equal to 0. And then we're going to go ahead and take a step over to the left side of B of x. And we did the same thing. We took the sum of the moments at A, and we said that the applied moment at A, or the internal moment at A from the fixed support, plus the 1 kilonewton times 5 meters from the By force, and that's all going to equal to 0. And that comes out to the moment at A internally is equal to 5 kilonewton meters clockwise. And then we go ahead and take the sum of the forces in the x and say that the 1 kilonewton from B of y plus A of y is equal to 0. And therefore, A of y is 1 kilonewton going downwards. And then again, for thoroughness, the sum of the forces in the x is 0, and therefore A of x is 0.
Alright, well, welcome back again. So after we found out all the forces in each support, now we're going to move on to the shear moment diagram. As you can see, I've redrawn our problem right here, and the distances apart are 5 meters. So with our forces being 1 newton, you have your shear diagram over here where you have shear from A to C at negative 1 kilonewton, I guess. And your moment diagram, it's also pretty simple, where you start off with a 5 kilonewton per meters to a negative 5 kilonewtons per meter at C, and then from there it's a constant negative 5 kilonewtons per meter all the way to point D. And just so we don't have to repeat this step again, this is actually the moment. Well, it's a moment diagram divided by EI, so it's your deflection diagram. That makes it easier to transition to our next part. Okay, so now we're going to move on to the transformation from the actual beam to the conjugate beam. And the way I split it down here is we split it into 2 parts. 1, to see how the supports transform, and 2, how the loading changes. So on this side, we have how the supports change, and essentially it's just a mirror image of itself. Your fixed support turns into a free end. Your internal hinge will turn into a roller. The roller will turn into an internal hinge, and then your free end will become a fixed support. Like I said, it's just a mirror image of itself. And here, this is the loading. And if you remember, this is our moment diagram, or our deflection diagram, to be more precise. This will become your loading diagram in the conjugate beam. And as you can see, all the loads point away from the beam. So your negative moment is a negative load, and your positive moment is a positive load. So that's it.
Doc. We're going to go ahead and proceed with our problem from where Yuli left off last time. And we're going to take the conjugate beam with its loading of the curvature diagram. And we're going to go ahead and split it at the new the point C there. And we're going to start over on the left side. And we're going to take the moments at C is equal to the minus 1/2 times the 5 times the 5. So that's the 5 of the distance and the 5 kilonewton meter over EI. And that's the area of the triangle. and that's going to be times its moment arm, which is 5 plus 2/3 of 5, and that gives you the area times the moment arm, and then plus the other triangle, which is the same thing, but it's going to be a different moment arm this time since we're about C, and then we're going to subtract the by times 5, and that all equals 0, and when you do the math, it all comes out to by equals 16.67 kilonewtons times meters squared over EI, and that's downwards. And then we're going to go ahead and take the sum of the forces in the y. It's going to be equal to CY minus BY, and then it's going to have the two areas under the triangles, but those two, as you can see, cancel since they're symmetric. And then so CY equals BY, and it's going to be 16.67 kilonewtons times meters squared over EI. That's going to be upward as drawn. And then we're going to go ahead and step over to the right side of the problem, and we've got that drawn for you here. And we're going to go ahead and take the sum of the moments at D is equal to CY times 5, which is our distance here, plus the 5 times 5, which is the area of the curvature diagram, times the 1/2, and then plus the moment at D, and that all equals 0. And that gives us the moment at D equals 145.83 kilonewtons times meters cubed over EI, and that's going to be in the clockwise direction. And then we're going to proceed to take the sum of the forces in the y, and we're going to say that that equals the minus CY plus DY, and then minus the area, and that all equals 0, and therefore dy equals 41.67 kilonewtons times meters squared over EI. And then just for thoroughness again, the sum of the forces in x is equal to 0, and cx equals 0, and dx equals 0.
Oh, hi, didn't see you there. So I guess let's finish up this problem. We're going to move on to the last part, and this is the part where we're trying to find the rotation at B just to the left and the rotation at B just to the right. So if we move on this side, we have the free body diagram right before B. So you have the distributed load acting on it, plus the force that we're trying to find, BYL. And when you take the sum of forces in the y, you get that BYL is equal to 12.5 kilonewton meters squared divided by EI. And that's pointing downwards. So your rotation at BL, which is equal to your force at B, is equal to negative 12.5 kilonewton meters squared over EI. And as you step over here on the right side, we have the same free body diagram, except this time it's just right after B. So the force at B that we calculated previously is incorporated into this, as right here, your 16.65. And the same thing, you take the forces in the y, and you end up with BYR of 4.17 kilonewton meters squared over EI in the positive upward direction. And as you can see here again, your rotation at B right is BYR, 4.17 kilonewton meters squared over EI. And if you remember from Tim's talk, moment at D was equal to 145.83 kilonewton meters cubed over EI, and that is your displacement at D, which is one of the things that we were trying to find to begin with. And those are three objectives that we had for this problem. So thank you for watching, and also congratulate our camera woman, Sam.